You see these massive airplanes in the sky all the time, right? But have you ever really stopped to think about how something that enormous can actually defy gravity? I mean, it can feel like pure magic, but the reality is all about some pretty fascinating and surprisingly simple physics. And just to give you an idea of what we're talking about, a fully loaded jumbo jet can weigh over 300 tons. That's like stacking hundreds of cars on top of each other. It's just a staggering amount of weight to get off the ground, let alone keep hanging up there for hours on end. So yeah, that's the big question, isn't it? How in the world is that even possible? How does this giant metal machine create enough force to lift itself up into the sky? Well, the answer is a lot simpler and way more interesting than you might think.
All right, so to get to the real answer, we've got to start by unpacking the explanation that most of us probably learned back in school.
I'm sure you've heard this one before. The idea is that the top of the wing is more curved, so the air has to travel a longer path, which makes it speed up. This faster air creates lower pressure, and boom, the pressure difference creates lift. It sounds totally logical. But here's the thing, it's not the full story, and it's actually based on a pretty flawed idea. And this is where that common explanation just completely falls apart. The myth is known as the equal transit time theory, and it's exactly that, a myth. There's no law in physics that says air molecules that split up at the front of the wing have to magically meet up again at the back. The real reason is much, much more direct. Wings work by pushing air down, period. And that downward push, that's the key. This brings us to the most important part of this whole explainer. Let's really focus on the fundamental action that makes flight possible. Seriously, if you remember only one thing, let it be this. Forget everything else for a second. An airplane flies because its wings are shaped and angled to shove a massive amount of air straight down. At its core, it really is that simple. And you know what? This isn't some crazy new theory. It's based on one of the most basic laws of physics out there, Newton's third law. The wing pushes down on the air, that's the action. In return, the air pushes up on the wing with an equal and opposite force, that's the reaction. And that upward push, well, that's lift.
And the really cool thing about this explanation is that it works for everything. It explains why even a simple flat board can generate lift if you just angle it right. It explains the classic curved wings we're used to seeing, and get this, it even explains how stunt planes can fly completely upside down. Because as long as the wing is angled to push air down, it's going to generate lift. The shape helps make it more efficient for sure, but it's not the main event.
Okay, so I can practically hear you thinking, but wait, what about that whole faster air, lower pressure thing? It's not totally wrong, it's just not the cause of lift. So let's put Bernoulli's principle back in its rightful place. First things first, let's be super clear. Bernoulli's principle is absolutely a real thing. It's a fundamental concept in fluid dynamics, and yes, faster-moving fluids do exert lower pressure. The principle itself is totally correct. And it's also true that on an airplane wing, the air on top is moving faster, and the lower pressure it creates absolutely contributes to the total lift, so it's definitely part of the equation. But this is the million-dollar question that the old textbook explanation never gets right. Why is the air moving faster in the first place? It's not because it's in a rush to catch up with the air on the bottom. That's just not how it works. And this is where it all clicks into place. The cause is the wing pushing the air down. That's Newton. The effect of that downward push is that the airflow gets accelerated over the top surface, and that results in the lower pressure that Bernoulli's principle describes. See the difference? Newton is the cause, Bernoulli describes an effect. So now that we've got the physics down, let's look at how pilots actually use it. How do they control how much lift the wings are making at any given moment? They do it with something called the angle of attack. It sounds technical, but it's really simple. It's just the angle at which the wing is tilted as it meets the oncoming air, and it's one of the most critical factors in flying any airplane. So here's how it works. At a low angle, the wing is deflecting a little bit of air down, which creates some lift. As the pilot increases that angle, the wing deflects more air down, which creates more lift, and this is what you're doing during takeoff. But, and this is a big but, there's a limit. If that angle gets too high, the air can't smoothly follow the wing's surface anymore. It separates, lift suddenly disappears, and the plane enters what's called a stall. Okay, let's wrap this up and bring all these pieces together into one simple, clear picture. So here's the complete picture, the big takeaway, the core principle. Wings push air down.
The force that lifts the plane is the equal and opposite reaction that Newton's third law gives us. The pressure difference that Bernoulli describes, that's a real effect of that action. And the control knob for this whole operation is the pilot adjusting the angle of attack.
So the next time you see a plane way up in the sky, remember this. It isn't floating on some magical cushion of air. It's not cheating gravity at all. In fact, it's actively and powerfully engaging with the air, obeying the fundamental laws of physics with absolute precision. I think this quote just sums it up perfectly. Flight isn't about floating. It's about climbing. An airplane literally climbs through the sky on a ladder it creates for itself by continuously pushing air down. And that, my friends, is how a 300-ton machine really flies.